Hi, so today I'll be talking to you about a Div2D problem or Div1B problem. This is one of the easier end problems, and this is a great way to demonstrate how to hash while using strings. And basically what this problem is asking for you, I'll just go through it very basically, is given a string S. So this is the string S. You're trying to find a way to permute S, so maybe S prime, such that there are a maximum number of occurrences of T in this string. So why do I make this T like this? Why do I not just make T's, like this? Because first of all, they're asking you for the number of substrings, number of occurrences of T as a substring in S. And usually substrings don't have to just look like this. They don't have to just, be like T, 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 like, in the string S. So if this is like, if T is ABC and S is ABC, 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 obviously these are not numbers. You don't need to just, you don't need to just have these like just connected together and together. Sometimes you might have like ABA, and over here you would have a substring and you'll have another substring over here, and this would be T1 and T2. So they could probably chain with each other, but we never know until we solve this problem. So when we actually see this problem is basically asking you for the way to permute S such that there's the maximum number of T's available in this problem. So to start off, let's look at an example. So over here we're given that S is 101, 101, and let me tell you, in this problem, all that matters is the count of ones and count of zeros. It doesn't matter of the order of ones and zeros, because you can eventually rearrange S and permute it in whatever way you want. It doesn't matter. So all we need to know is that there's 4 ones and 2 zeros. So if you look at T over here, this is 1, 1, 0. How do we construct S such that there's maximum number of T's? So one way you would do this, because you can't overlap, is that you could just do 1, 1, 0, 1, 1, 0. And in fact, this does work, because you see there are 4 ones and 2 zeros, and this is your answer. So your answer would basically be that there would be 2 T occurrences, and this is your output. And for this one, you can see over here, we want to find the maximum number of occurrences of 1, 0, 0, 1, 1 inside of this string. And as you can see in this string, there's 4 ones and 4 zeros, and the only way we can do this is, by making it like this, right? We can only fit one of these, because the other one requires another 3 zeros, and we only have 4 zeros, so we can only fit one of them. And this is one of your possible answers. There's multiple answers that are possible, but this is one of the answers that's possible. And you can see for this one, of course you can't fit your answer would be there would be no occurrences of T, because there's no way to fit 1, 1, 1, 0, 0 inside with your S string as 1, 0. So you can do whatever you want. You can do 1, 0, 0, 1. It doesn't matter. Just make sure you're just printing in the the original. You're keeping the number of ones and zeros consistent in your permutation of S compared to the normal S value or the original S value. So with that basic intro, let's see how we're able to fit these T's inside of this S prime substring. So if you think about it, as we've seen in this example, we would just basically chain them 1, 1, 0, 1, 1, 0 together, and we would get this answer. But in most of the cases, we actually won't be getting that, because if you, for example, if let's create a new problem. If S was, let's see. If S was 1, 1, 0, 1, 0, right? And T is 1, 0, 1. What we would get in here is the answer, or S prime, would actually be 1, 0, 1, 0, 1. So as you can see, this is your first T, this is your second T. And the reason is, if you put these 1, 0, 1s back to back, if you put these back to back as you did in this example, you'd end up consuming more ones than you would need. And of course, there's only 3 ones available. You only need, you can only do it this way in order to satisfy this arrangement of 3 ones, and 2 zeros. So if we want to construct a solution, this kind of starts to give you an insight. You want to try to put the t as early as possible in front of the previous t. And if you can see in this case, your t was actually 110, and there's no way to overlap 110 in any way with 110 itself. So the only way that's possible, see, you can't even do it here. The only way that's possible is just by basically overlapping it by just putting it, back to back. So you can't really have an overlap in this case. But then in this case, of course, you can optimize by basically putting these 101s back to back, and you're able to save an extra one. So basically what we're trying to do in this problem is we're trying to put the t as early as possible in front of the previous t. So this is our t. If you can overlap, if all of these characters are equal, if they're the same like string, same string, then you can overlap them together. So like for example, this is 10 10 10 10 10. We can overlap it here, of course. We can do 10 10 10 10. That's a feasible option, but a better way to do it is by putting it here, 10 10 10 10. And what this does is that it saves us 6 letters. And you can see this is definitely more optimal, because what we're trying to do is we're trying to, efficiently use up the characters of S and fitting in the maximum number of T. So if we use up, if we use up more letters, like if we put it over here, then we have less 10s to consume if we wanted to put maybe an extra sequence. Maybe we might run out in the future. But obviously it won't hurt if we just put it as early as possible, because we would just have extra letters. If there's spares at the end, we can just concatenate them at the end without having to add an extra t. So that's what we would realize. So there would be no harm if we put it earlier, if we put the second t as early as possible, and overlap it with the first t. But the real question over here is, how do we actually do this? So we actually use a technique called hashing. So if you would just do this naively, what this would look like is, if you had a string like this, you would check, okay, for I is equal to 1 through n, so this is 1 through n, check if t of 1 through n fits on t of I through n, so basically without the last letter. So for example, you're just checking if t basically itself overlaps on here. So this would be t, just checking if it overlaps. Instead of n, this would be minus 1 plus n. This would actually be n minus 1 plus I minus 1. So minus I plus 1, right? So we're just checking if 1 through n minus I plus 1 would equal to the substring of t of I through n. So we're basically just checking if these two substrings are equivalent to each other on each step. But if you actually check out the analysis of this algorithm, this is an O of n factor, and over here we're progressively checking less and less letters, but at the same time we're still checking overall an O of n divided by 2, because we start with n and then we get less and less and less and less, and overall that's still going to be a pretty big number, So on average we're still going to have n divided by 2 letters that we're going to have to check through every time you match 2 strings. So like t over here, like even though at the beginning you're matching t letters, you might get t minus 1, t minus 2 all the way to 1, but on an average you're still matching t n divided by 2 letters. So where n is basically the size of substring t. So this is way too inefficient. O of n squared. This would be, if you look over here, the size of t is 50,000. This would be 25 times 10 to the power of 6 divided by 2. This is 5. So this should be 10. This is way too big, so we can't do this solution. So what we're going to do is we're going to use the help of hashing, right? So just to motivate you on hashing, let's first look at a string like this. So if we have 1 0 1 1 1 0, right? So what is the earliest place we are able to place t in front of itself? So as you can see over here, first let's start off over here. Let's check. So this is the brute force method. This one, you know, all of them match, but of course this is not possible because we can't overlap a string with itself this way. So this won't work. If we do 1 0 1 1 1 0, we're basically going to go ahead and check, you know, these characters, right? This is fine. This is different, so this won't work. Now let's do it again. 1 0 1 1 1 0. And this one, of course, doesn't work. You have a 1 and a 0 here, so this won't work. And now finally we have 1 0 1 1 1 0. 1 matches with 1, 0 matches with 0. Correct, this one works. And this is your final answer. But the problem, of course, as I said previously with the solution, is that it's too slow. It runs an O of n squared over 2, where n is the size of t. Or if you wanted to do, you could just do size of t squared over 2. Doesn't matter. So this actually kind of motivates you a little bit about hashing, because if you actually think about it, what we're doing in each step is we're iteratively, so for the first step, we're just comparing, you know, nothing with nothing. But for the first step, what we're doing is we're basically comparing this side of the string with, you know, we're comparing this side of the string with this other side of the string. So we're basically comparing this side of the string with this side of the string. And on the second step, we're comparing, as you can see over here, this is our overlap. 1 1 1 0 is overlapping with 1 0 1 1 1. And basically, effectively, what we're doing is we're comparing this half of the string with this half of the string, and then we're going to go smaller, so 1 0 1 versus 1 1 0, and then even smaller, 1 0 and 1 0, and then finally the last two, which is 1 and 0. And as you can see, the only one that worked was when we compared these two letters with these two letters. So 1 2 3 4 5 6. So 1 2 and 5 6 matched, but this one didn't match. So basically what we're doing over here is we're basically effectively, if you actually think about this, is the same thing as comparing. You know, first we're comparing these. 1 is not equal to 0, so that doesn't work. If you go over here, 1 0 is equal to 1 0, so this definitely works. And we don't need to check the rest because the rest, well, I mean, we do need to check the rest though, because we want to try to see if we can put it earlier. So 1 0, this doesn't work. 1 0 is equal to 1 0, it does work. 1 0 1 and 1 1 0 is not equal, so this doesn't work. And 1 0 1 1 is not equal to 1 1 1 0, of course. So this is our only answer. And this is also the earliest possible way to place it, because the second earliest possible way to place it would just be just concatenating it right at the end. And of course we want to save 2 letters as much as possible, because still 2 letters, you can use it on somewhere else probably. So if you think about this in terms of hashing, what we're actually doing is, of course if we do it with you know, our previous method, this would be an O of n squared solution. But if we do hashing, every time we're basically, the goal is we're basically representing a substring as a number, right? So instead of actually comparing 1 0 to 1 0, we're comparing the hash of 1 0 to the hash of 1 0, which indeed is true. It's correct. And when we compare these two, you know, the hash of 101 is not the hash of 110. So this one is not correct. And of course, there's these things called hash collisions, and of course you need to account of that. But in this case, I will just, to make it simple, I won't really care about it for now. But in larger cases, there's definitely, as you know, t gets larger, there's going to be more hash collisions. So even if they're equal, you might want to check, you know, if indeed the first 2 letters is equal to the last 2 letters. So that's just a nice thing to put in your program. But now to the hashing part, right? How do you represent a string, right? So if you actually represent a string in terms of a number, let's define a hash function, right? Let's call this string ABCD, right? So the hash function is actually a times, so this is ABCD would be letters, or, you know, yeah, a times prime 1 to the 3rd power. So 1, 2, yeah, plus b times prime 2 to the 2nd power. C times prime to the 1st power times d to the prime to the 0th power. So that's basically just 1. And we're going to do a mod of a 2nd prime. Let's call that big P, right? Because what we're doing over here is that this number would probably be huge. So in order to process it and to check, you know, more efficiently, without comparing two huge integers together, we're just going to take the mod of a larger prime together. And if you look, and in my solution, what I did was I chose p as 37, and I chose mod as some random prime number that I just saw off the internet. So these two in this problem definitely works, but you can do whatever you want. You can choose any two primes. So the goal over here is that polynomial addition is much faster than comparing two different strings by checking each of their letters one by one. And if you take a look over here, if you take a look over here, if let's say you're trying to compare what's the earliest position over here, you're going to start with the first two letters and the last two letters. So that's your hash for 10, and that's your hash for 10, right? Or in technical terms, this would be hash of t from 1 to 2, and hash from t to, let's label this 1, 2, 3, 4, 5, 6. Hash of t from 5 to 6. But then as we transition over to hash of 101 and hash of 110, because basically what we're doing is we're effectively adding one number, we're actually transitioning to hash of t of 1 to 3 and hash of t to 4 through 6. And our goal is to try to make this transition as efficient as possible. So preferably make this O of 1. So every time we make a transition, it's going to cost one operation, rather than last time when we're comparing these two strings and that costs approximately O of n times n squared total for every single string we did. So over here, if you see the representation of hash of t12, the hash of t of 1 to 2 is basically just t of 1 times, let's see, prime to the first power plus t of 2. And if you look at hash of t of, 1 to 3, what we're doing is we're actually doing hash t of 1 times prime to the 1 plus t of 2 times prime to the 2 plus t of 3. Let me see. Sorry, this should be prime to the second, and this should be prime to the first, and this should be prime to the 0th power. This should also be prime to the 0th power, just for illustration purposes. And if you actually look at this, what we're doing is, of course, we're just taking the primes of each of these. We're just multiplying the string with a polynomial that represents our hash. And this is mod p, and this is also mod p, which is our big prime. And if you actually look at this, you can actually represent this as a function of h of t of 1 to 2. If you actually notice this is actually h of t of 1 to 2 times p plus t of 3, right? Take a moment and look at it. So over here, if you can actually see over here, our state transition is literally O of 1 because we're just taking our last value. And we're multiplying it by, we're taking our last value over here, and we're multiplying by p, and we're adding in the third value with a 0th degree coefficient. And make sure we also mod p over here so that we're able to get our answer. Now, if we actually think about this other case, right? So how to transition from 5 to 6 to 4 to 6. Let's see if that works as well. So if we're doing, h of t of 5 to 6, what we're doing is we're doing t of 5 times p to the 1 plus t of 6 times p to the 0. Now, for our next value, so if you see over here, what we're doing is we're trying to, so this is 5 to 6. Now we're actually adding another value, 4 to 6, right? We're adding an extra number. Last time we were doing 1 to 2, but now we're checking 1 to 3. So we did that by basically doing an O of 1 transition time. So this is O of 1 because we're just adding in constants and we're not doing any operations other than addition and basic addition and subtraction. So over here, if we want to see what 4 to 6 is, let's rewrite this expression, right? T to the 4 times p to the second plus t of 5 times p to the first plus, let me see. Yeah, and then t of 6, right? So that's basically the way we're able to represent this. And if you actually see over here, what we're doing in this case is we're doing something really similar. If you actually notice this, t of 4 to 6 is basically just h of t of 5 to 6 plus t of 4 times p to the second power. And what we're effectively doing here is we're basically just taking the last value, and unlike the last time where we basically just took t of 1 to 2 and we multiplied this by p, our prime, plus the next term, over here we're taking the next term and we're multiplying by the prime multiple times, and we're just taking our last term and just adding the extra term to it. And if you actually see these two, this value, so over here, as you can see, we're just multiplying by a constant, so this is O of 1, and this is also O of 1, so this total operation is also O of 1. So as you can see over here, what we've basically demonstrated, just to summarize what we did over here, was we demonstrated that we were able to, calculate the hashes of, 1 to 2 and 5 to 6, and then turn it into a hash that compares 1 to 3 and 4 to 6 at O of 1 time, because all we're doing is we're just adding a constant to both of our expressions, and we took a mod and we were able to calculate our hashes. And what we can do now is once we get these new hashes, h of t of 1 to 3, which is basically a result of t of 1 to 2, as well as our hash, which is t of 4 to 6, which is a result of 5 to 6 plus an extra term, we can just take these two values and we can just readily compare them, 1 to 3 and 4 to 6. 1 to 3, are they equal? So 1 to 3, the hash value for this would be some number a. 4 to 6, this would be some hash number b, and we would check if they're equal. If they're equal, then we know that 101 is equal to 110, and if they're not equal, then we know that these two numbers aren't equal. And the only exception is if there's any collisions, but the probability of collisions is so little that it's not really present in the big O notation. So basically, we can do this. We can go from 1 to 3 to 4 and 4 to 6, and then we can do that operation again. We can do this operation. We can add, the h of 1 to the third term plus p plus t to the 4, and we would get the hash for 1 to 4. Same thing as here. We can take our hash of 4 to 6, and we can add t sub 3 p to the third power, and what we would get is we would get the hash from 3 to 6, and now we can compare it again. Is 1011 equal to the same thing as 1110? No, they aren't. So now you know that you can't overlap them at this value, and we can keep doing that over and over again, and we would just get every time we do this hash comparison, we would just do an O of n operation, because we're just we're doing this operation n times. We're checking if hash of 1 is equal to hash of 6. No. Is hash of 1 and 2 equal to hash of 5, 1 and 2 and 5 and 6? Yes. So this is a possible answer. Let's check if we can go further. Is hash of 1 to 3 equal to hash of 4 to 6? No. Is hash of 1 to 4 equal to hash of 3 to 6? No. Is hash of 1 to 5 equal to hash of 2 to 6? No. So that's our only answer. We can only go up to the fifth term. So after we've done this process, since we now have an O of n solution, now all we're going to do is we're basically just going to go through this iteration, this O of n iteration, and we would check the minimum, the minimum value in the second hash, the minimum boundary of the second hash, where we can go to. And if this second boundary we're able to get through, we're able to get through, for example, over here, we're able to get to, so the second hash over here, the minimum boundary is 5, because we can't go any further. We can't go any further and overlap with the first hash. Then that's the answer. That's the exact place that we're going to place the second value on. And this would make sense because if you look over here, 101110, the way we would overlap is 101110, and we would overlap it exactly like this, because these two values would be together, and our overlap would look something like this. 10110, and then 10110, right? So you would have one of them over here, and you have the second one over here. So that would be our answer. So after we're done with this, now we've consumed 2 t's using our hashing method. We've been able to efficiently consume 2 t's using our hashing method. So now what do we do with these, the leftovers? So basically the outline of this is that we're basically, we have our string s, right? And we have a string t, and we're trying to permute s such that, s prime has the maximum number of t's available. So every time we would just do this algorithm multiple times, right? You would take this t, find the earliest position on t that you can, overlap t with itself, take the earliest position of t, overlap it with itself, and keep doing that until you get a cascade of t's. And you're going to keep doing this. So every time you overlap a t, so let's say you have 1 0 1 1 0 1 0 1 0, every time you take a 1, you take off, you keep a running count, so int num of 1s is equal to, you know, k, and int num of 0s is equal to L. So this would basically be the number of 0s and 1s that are present in our string S. And then we would take these two values. Every time we run through a 1 in our merge, in our sequence, we would deduct 1 from the number of 1s. Every time we meet a 0, we would deduct 1 from the number of 0s. And we would keep doing that until we run out of 0s and 1s. So in this case, if we had a string S, and we maybe had, like, let's say 30 1s and 15 0s, we would, go like 1 0 1 1 1 0, 1 0 1 1 1 0, and of course we would place this again over here. So 1 0 1 1 1 0. So you have 1 2 3 4 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29. So you have 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 1, let's see, 1 4 7 10 13 16 19 22, and then 25 26 27 28. Okay, and then right over here you have 29 and you have your 30th. Now you've run out of 1s. You can't put an extra 1, right? So now what we're going to do is that since we have 30 1s and 15 zeros, we've depleted all of our 1s, right? So let's count the number of zeros we've used. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 5 zeros left. So what are we going to do? Of course, we don't want to put it in between any of these because that would sacrifice the number of t's we would be able to get in our substring. So all we're going to do is we're going to take these zeros and we're just going to concatenate them at the end of our string. And that is your final answer. If your initial string S had 30 zeros, 30 1s, and 15 zeros, and you wanted to create a permutation of S, which is S prime, such that, so this is your S prime, such that S prime has the maximum number of substrings T that it can fit in here, where the substring of T in this case would just be 1 0 1 1 1 0. And this would be your final answer. So problem solved.